Alright, this is Physics 1C for October 15th. Tonight we're going to be talking about the force between two parallel conductors, and then we'll talk about the field of a circular loop, and then we'll talk about Ampere's law, and we'll look at some applications of Ampere's law. Ampere's law is our third Maxwell equation, I guess, because the first two were Gauss's law for electricity and then Gauss's law for magnetism. Okay, so force between parallel conductors. So let's say that you have a wire. There's a wire, and let's say that it carries current, and let's say the current goes in this direction, and let's call that current I1. And let's say that next to it we have a parallel wire that also carries current. I guess we could use the same color. So we have another wire over here, and let's say that they lie parallel to each other, so that the distance between them is fixed. We'll call this one. We'll say this one has a current that we call I2. Let's say the distance between the wires, so from here to here, let's say the distance is A, and it's the same distance all the way through, so parallel meaning that they maintain the same distance from each other. Let's also say that the lengths of wire that we're looking at here, the wires are longer than this, but maybe the length is just, we'll call it L. So they both have a length L. And what we'd like to do is we'd like to think about the force that the first wire can put on the second wire, due to the fact that there's really two things that are working for this here. Last time we derived the magnetic field, so B for magnetic field, created by a long wire, like this one here, and we said that it was equal to mu naught multiplied by the current flowing in the wire, divided by 2 pi, and then you have to multiply by the distance that you are away from the wire. So we know, for example, that the wire I1 produces a magnetic field, right? And if we come down here to where wire 2 is, then there's going to be a magnetic field at this location. Can you tell me what direction does the magnetic field, like right here, does it point into the page or does it point out of the page? I want to know the magnetic field due to wire 1 at the location of wire 2. What direction does that point? I see one answer. One person says out. What does everybody else think? What direction does the magnetic field of the upper wire at this point right here, is it going to be coming out of the board or is it going into the board? Okay, a few people are saying in now. All right, and just to remind you of how you can figure that out, what you do is you point your thumb along the direction of wire 1, and then your fingers rotate in the circular magnetic field that it's going to be created. So at this location, the field due to this is going to be pointing into the board. So there's going to be a magnetic field all along this wire here, and it's going to be, we'll call it B1. It points into the page. Above wire 1, the magnetic field would be coming out of the page, so we use dots like this. Okay. So that's the magnetic field location in that direction. Now, we also know that given a magnetic field and given a wire that carries current, there's going to be a force, right? That's the other half of this. The magnetic force on a current-carrying wire is equal to the current flowing in that wire. I don't know why I wrote it like that. The current flowing in the wire times the length of the wire, which you write as a vector that points in the same direction as the current. You cross-product that with the magnetic field. IL cross B, that gives you the force acting on this wire down here. So what I would say is that there's going to be a force. We could call it the force of 1 on 2, or I'm just going to call it F2. And that force would be equal to the current I2 times the length here, which we're saying is L. And we need to multiply that times the magnetic field B1. They're at right angles to each other, so we'd also multiply this by the sine of 90 degrees. I2 points this way. The magnetic field goes into the page. They're at right angles to each other, so we'd have this term right here. Okay. And what direction would that force point? Would it point up toward the wire, or would it point down? Okay, one person thinks that it's up. What do y'all think? What direction is this force going to be? Is it going to be upwards or downwards? Those are the only choices because this force has to be perpendicular to both the magnetic field and the wire. Yeah, it's up, right? So there's going to be a magnetic force, and it's going to point this way. It's going to point this way kind of all along the wire, really. So that's going to be the force that we call F2. Now, we can combine these two ideas together now and say that this force, F2, is equal to I2. That stays the same. Change the way I'm sitting because it's making these look kind of weird. So this force, F2, is going to be equal to I2 multiplied by the length. But B1, the magnetic field created by wire 1, is going to be equal to, according to our equation here, it's mu naught multiplied by I1, and then we have to divide that by 2 pi, and you have to multiply by the distance here. Okay. So, we get this expression that we're going to rearrange a little bit here. I'm going to say that the force, I'm going to divide the length on this side over here, and what we'll have left with is mu naught times I1 times I2 divided by 2 pi times A. And it turns out that this same force is also going to exist on the upper wire as well. And it's going to point this way. The reason for that is because the magnetic field, let's use a different color for this. The magnetic field of wire 2 at this location up here is going to be coming out of the board. You can convince yourself of that by using the right-hand rule. We can call this one B2. And the force would point downwards. Due to Newton's third law, these forces have to be equal and opposite to each other. So since the upper wire pulls wire 2 up, the lower wire has to pull I1 down. Right? So you could say in this case that because the wires are carrying current in the same direction, this force ends up being attractive. If one of the wires had its current reversed, the force would become repulsive. So I'm going to drop this subscript here and just say that this is our general expression for the force between two parallel wires. And we say that the force is attractive when the wires carry current in the same direction. And it's repulsive when they're in the opposite directions. And that's it. The force per unit length, two wires that carry current. Does anyone have any questions? Does that all make sense? Yeah, so if the wires were carrying current, like if one wire was going this way and one wire was going this way, then the forces would be repulsive. And I can show you a demo of this. I don't think I need to turn the sound on for this one. I don't really think there is sound of any real kind. We have this same demo at our school. So, yeah, here we go. There's a question. Let me answer this question real quick before we start this. What would change for the equation if they are both repulsive? You mean if they're both have current to the left? What did you mean by both repulsive? You mean like in this case? Nothing. Nothing. It's the same equation. A represents the distance between the wires. This represents the size of the currents. Force. None of these things change. Nothing changes. Okay. Let's watch this demo. So they've got this battery right here, which kind of looks like a car battery, connected up to these two wires here and here. And yeah, let's see what happens. It's a pretty short video. So there they're being repelled, and there they're being attracted. Repulsion. Attraction. Series, okay, I mean, I don't know if this makes sense immediately when they say series, but when they say series, they mean that these wires are connected in series so that the current goes up this one and then down this one, so the opposite direction, right? And when they're in series, they repel each other because the current flows in opposite direction, and when they're in parallel, same direction, they attract each other. That's pretty much it. We watch out the rest of the video here. I don't think there's anything else. Okay, so y'all have any questions? We'll do a quick problem. All right. So we have two straight parallel superconducting wires that are 4.5 millimeters apart. I don't know why it's important that they're superconducting. They carry equal currents of 15,000 amps in opposite directions, a huge amount of current. What force per unit length does each wire exert on each other? All right, we don't know the length, we just want to find the force per unit length. This is what we're looking for. And the equation we just derived was mu naught I1 I2 divided by 2 pi times the distance. So the value of mu naught is it's a magnetic constant. It's equal to this. Four pi times 10 to the negative 7 Tesla meter per amp. Each of these currents is the same. They're going in opposite directions, so we know that they're going to repel each other, so this is going to be a repulsive force that we find here. So 4 pi times, okay, they're 4.5 meters apart, 15,000 amps, so we do 15,000 amps. They both have the same current, so we're just going to square that. We divide that by 2 pi, and then times the distance between the two of them, which is 4.5 millimeters. That's it. What do y'all get if you calculate that? I don't know. This is what I got by doing it in my head, but it's probably wrong. Might be 10 squared. I don't know. What do y'all get if you calculate this? But you got 10,000? Oh, because it's 15 squared, so you end up multiply by 3 again. Okay, yeah, sure. That makes sense. Forgot that this was squared right here. Okay, so 10,000. And that's going to be in units of newtons per meter. How does this work out to be newtons per meter? So we've got the units of this are Teslas times meters divided by amps times amps squared, and then divided by meters. You know what? Is that unit right? Let's see. So that's our equation for the magnetic field. So if we rearrange it, mu naught would be equal to B times R divided by I, and there's a 2pi. So it's Tesla meter over amp, right? R goes here, I goes there, okay. So amp squared, amp. So it looks like these cancel. One of these cancels, so we end up getting Teslas times amps. So now we need to remember what a Tesla was. To remember what a Tesla was, you go F is equal to Q times V times B. So a Tesla is force divided by Q times V, which is Newton divided by meter per second times coulombs, which is Newton, because coulombs per second is amps. This is newtons per meter amp. So you plug that in here, so this ends up being newtons per meters times amps. So you get what we wanted. You get this. You get newtons per meter. Okay, anyone have any questions? So, I don't know if y'all know this, but sometime, I believe it was in 2019 in May, so little over a year ago, they redefined what the kilogram was, and the definition of the kilogram actually comes from a balancing of wires like this, and finally tuning the currents to a certain amount that will balance out the weight of 1 kilogram. And in so doing, you can end up defining the kilogram in terms of some fundamental constants. Did you guys know about that they redefined the kilogram? Had you heard of that before? Yeah, so the kind of the 3 fundamental units that we think about are mass, length, and time. And time is defined based on atomic clocks. Length is based on the distance that light travels in a second. And so those two for a long time have had kind of a fundamental connection to fundamental constants like the speed of light, for example. But the kilogram is now defined in terms of what's called Planck's constant, because something about the way in which the current moves is related to Planck's constant. Planck's constant. Sometimes I feel like when I say Planck, people don't know who I'm talking about, but yeah, anyway, so it uses what's called a Kibble Balance. And the Kibble Balance, at its core, operates off of balancing wires with an applied force. So you obviously get a force out of this, right, related to this, and you could then balance that force against a weight that weighs a kilogram, and you can use that to define the kilogram in terms of Planck's constant. They also actually, and this is one thing that's interesting. Okay, when I say Planck's constant, I keep saying it. Do you guys know what it is? We use the symbol H for it, and it's equal to 6.63, some other things. It's like 6.626 or something like that, times 10 to the negative, I think it's 34, and then it has units of joule seconds, right? Joules times seconds. But then within a joule, right, a joule is kilogram times meters squared per second squared. So you do that times seconds. That's what the unit is, this thing. So within the thing is the kilogram, right? So what they did actually was they fixed this value. They fixed the value of Planck's constant to something. It's like out to like 9 digits. It's like 6.6. I think it's like 2.6. They fixed it out to 9 digits. So Planck's constant is no longer something that we measure, but it's defined, which I find to be kind of, it's a little weird because I don't know, it's only 9 digits, and maybe that doesn't matter to you, but there's things that we know more precisely than that, so I find that really strange. But regardless, that's what they did. So they defined Planck's constant, they set it to a specific value, and they used it to define the kilogram in terms of Planck's constant, using one of these balances. You can go read about it if you want to. It's called the Kibble Balance. You look at all the mathematics behind it and stuff like that. It's kind of fascinating. Okay, so anyone have any questions? All right, so let's talk about the field of a circular loop. And for this, we're going to use this picture here. It's kind of a good thing we can use this picture because every year when I try to draw this on the board, it's very, very challenging. Usually just use a prop. Okay, so we've got a wire. It carries current as shown. The x-axis is kind of coming out towards us here. The y-axis points up this way, and then the z-axis points that way. Our wire is confined to the yz plane. And, yeah, well, there it is. There's the wire. It carries current like this. It has a radius that we're calling A. It's centered on the origin. And we're going to try to find the magnetic field on an axis of the loop. So this is the center. The x-axis runs straight out like this. So we say on axis. We basically want to find an expression for the magnetic field at point P. And to do that, we're going to use the Biot-Savart law. The Biot-Savart law said that the magnetic field is given by mu naught divided by 4 pi multiplied by the current flowing in the wire. And then we need to do this weird thing of dl, that's the symbol your book likes to use, cross r hat. And then you divide that by r squared. And of course we need to integrate this thing. So this was called the Biot-Savart law. We use this to derive the magnetic field of a straight piece of wire. Tonight we're going to do it on this loop of wire here. Now, most of the hard part's been done in this picture. We've selected a point at the very top right here. And we've said that dl, right? dl is like an element of the wire. It's an arc length, little minuscule arc length. R is drawn from that little piece of the current down to the point P. So it's right there. And at the point P, then, what you have to do is you have to do dl cross r hat in order to figure the direction of the magnetic field. Now, they've already drawn it in here. But try to convince yourself that that direction makes sense to you. So point your fingers of your right hand in the direction of dl, and then rotate them from dl to r hat in this way. You should get that your fingers of your right hand are going to point kind of up like that, just as they did here. Sorry, the thumb. So you point your fingers this way with your palm facing towards r. You rotate your fingers from dl to r, and you should get a vector that points kind of like this. I'll give you a moment to look at that, because I think that's hard to see. It has to be perpendicular to the vector r, and it has to be perpendicular to the vector dl. So if you think about the fact that those two vectors make a plane, then maybe that'll make sense. That's a right angle, that's a right angle. Okay. You can get that part, we could solve the rest of this pretty simply. Okay, so we'll now use a kind of similar argument to something we've done in the past and say, we notice that the magnetic field points kind of up at an angle like this. But if we were to go to the opposite side over here, where the dl vector would point this way, and our r vector would go this way, you can see how this immediately becomes very hard to understand what I'm doing here, I think. But if we come down here, I would argue that now if we do dl cross r, we're going to get a vector that is kind of equal in size, but kind of not exactly opposite in direction, but opposite enough that the by's are going to cancel, while the dbx's will add. So this piece and this piece here are going to be equal and opposite to each other. Can you imagine that in your head? In spite of my horrible drawing here? You might even argue that you can just think about it and understand it, that if the magnetic fields due to this piece points that way, the magnetic field due to a piece on the other side is going to have to point back that way, and automatically the dby's are going to cancel out, and you're only going to have a dbx component, and that's what's going to happen here. Does that make sense? If you still can't see it, another thing you could do is you could argue it's like a mirror, right? If I was to take this entire system, okay, and I rotate it around by 180 degrees, you'd have to rotate this vector around by 180 degrees too, right? Does that make sense? So it's a mirror. It has to be a mirror on the opposite side because this is a circle. All right, so we know that the ddy's are going to cancel. Good. At least one person says they see the symmetry. All right, so the dby's cancel. So really all we're going to need to worry about here is dbx. So what's dbx equal to? So dbx is the x component of the magnetic field created by just this one little dl here. And it's going to be equal to mu naught times I divided by 4 pi. We need to do this dl cross r hat thing here. What we're going to get out of that is going to be the magnitude of dl times the magnitude of r hat, which is 1. We also have to multiply by the sine of the angle between the two of them, which I think is 90 degrees, right? The angle between this and this should be 90 degrees, right? Because dl is a vector drawn in the yz plane, and r hat is drawn well, from that plane to another point in the x-plane. I think it has to be 90 degrees, right? Does anyone disagree with that? You're not seeing? Yeah, it's kind of hard to see. It's definitely really hard to see. How else could I draw this that might make it easier to see? So what if we draw it in a plane like this? So this is our loop, let's say. And that's the center of the loop. And then the dl vector is going this way. And now we're going to draw a vector from here to some point that is kind of in front of us, right? But that vector, how to put this? What would the projection of that vector look like onto this plane? Imagine a shadow that's cast by a vector. So I draw a vector from here. I draw it out to the point P. Think about the shadow that that vector casts. Wouldn't it cast a shadow that would be straight down like this? Okay. So now think about this. Take that vector that I've drawn down here, which is unquestionably at right angles, and now imagine rotating this vector, which was originally the shadow. Take that and now rotate it up towards you until this arrow is pointing at you now, right? You'd certainly agree that if I point this arrow straight out of the board from this point, it would be a right angle. But I would argue that at any angle in between, it's still going to be a right angle. Does that help y'all to see that? Okay. All right. So this is a right angle right here. which means that when we do dl cross r hat, we're going to have just dl times the magnitude. Oh, let's go back to green. We have to dl times the magnitude of r hat, and then we multiply by the sine of the angle between them, which is 90 degrees. Which is good, because this angle, if there was an angle here, it would show up in the integral, which might make things a little harder. We're dividing that by r squared. And we're finding just the x component here. So the angle theta is drawn here, which we'll use to use trig, but it's also drawn here. And I would argue that the x component now, since this is theta, would be gotten by multiplying by the cosine of the angle. And now we merely just need to kind of turn this into an integral and set some limits, and we'll be good to go. So let's start filling in some of these details here. So the first one that I would want to do is I'd want to get dl in terms of some of the other variables in the problem. And I would say that because I have a circle like this right here, I could say that if I was to choose, for example, any portion of the circle and define the arc length of that piece to be s, I would argue that if the angle that it's made up here is, well, for lack of a better word, theta, that the length of the arc, s, would be equal to a times theta, as long as the angle is measured in radians. So taking this one step further, I would say that dl, a small piece of the object here, would subtend an angle d theta, and dl would be equal to a times d theta. So that's what we'll use to replace it there, saying that dl is equal to 80 theta. So in our equation now, we'll go ahead and do an integral now. So we'll say bx is going to be equal to, mu naught is a constant, I is a constant, 4 pi is a constant. Is r a constant? Is r a constant? Yeah, it is, right? R is the distance from this point to here, but because it's a circle, all those points are going to be the same, so we can pull the r squared out. Okay. What else do we have? We've got dl, which we said was equal to 80 theta. I know a is a constant, but I'm going to go ahead and put this in here. Sine 90 is 1, cosine theta. Is theta a variable? Oh, there's a problem here. I immediately should have realized that as I was saying it too. I can't call this theta, I have to call it something else. I have to call this like phi. Can you guys see why? Because theta is this, and theta is actually a constant, it's not varying. So I need to change this to 80 phi. Otherwise we won't be able to actually do the integral. In fact, in retrospect, what we'll see happens next, I didn't even need to do this. I didn't even need to replace dl. But, yeah, so cosine theta is not a variable, right? Cosine, this is also a constant. A is a constant. So really, we don't have to even do the integral here, at least not one that's very hard. So we end up getting mu naught I divided by, there's an a right here. There's still a 4 pi r squared. There's a cosine theta. And then that's all multiplied by the integral of d phi. And we'll just integrate this all the way around the circle from 0 to 2 pi. So we'll end up getting from this to 2 pi that will cancel with this one. So we'll get mu naught times I times a times cos theta. I'm going to rewrite cos theta in a second. Divided by, we get a 2 pi out of here that'll cancel out one of these. So it will be 2. 2r. And that's it. That's the answer. Now we'd like to have x show up in our answer. Let me just stop for a second. Does anyone have any questions? Yep, that's right. That's right. We didn't really remove an r, did we? It's just 2r squared. Thank you so much. Any other questions? Well, it's not exactly empty, is it? I mean, it's you know how to do the integral of x dx. You also know how to do the integral of a constant times dx, right? That's all this is. It's like a 1 or something. And this integral, sorry, I guess I could have done it out. Like, this would be mu naught times I times a. I don't know why I'm always so keen on skipping steps all the time. 4 pi r squared. I think it's just what physicists do. So this would end up being the integral. This becomes phi, and then we integrate it from 0 to 2 pi. Now we don't plug that in for theta because theta is fixed, right? It's a fixed value that's not going to change. Does that make sense? Okay. So we get this, and I want to now replace cosine theta and r. So we'll have mu naught times I times a. The cosine theta is going to become, looks like, I think, a over r, right? So we'll get a divided by 2r cubed. But then we can replace r. I think this will be our final answer. Mu naught I a squared divided by 2 times, so r cubed is going to be x squared plus a squared to the 3/2 power. Because r itself would be x squared plus a squared to the 1/2 power. Because r is this, and then x and a are right there. And that is also another right triangle. That's our answer. This would be the magnetic field of a loop of wire on axis. And there's a particularly interesting point for this that we can look at, which is that at x equal to 0, this equation becomes the magnetic field at the center of a loop of wire. And with x equal to 0, this just becomes a squared cubed, and you get mu naught times I divided by 2a. In addition to this, so this would be the magnetic field at the center of a coil. Let me go down just a little bit here now that we've got our answers. So this is the magnetic field at the center of a loop. And what we can do also is say, well, suppose that I have a loop of wire that then loops back on itself again and again and again and again and again, so that I have n turns. At the center of that loop, where the radius is a, then I could also just multiply this by n. Either equation, really, but this one is the one we more commonly do so with here. This would be the magnetic field at the center of a loop with n turns. We say turns for the number of times it turns around. Okay? Do you remember, I showed you a video of an electron beam that this person was curving in a circle? Do you remember that in that video, there were these big loops of wire that were kind of, well, parallel to each other in a way? I don't know if you remember this, but the device that he was using had on it a kind of, it was like a cylindrical apparatus, right? You had one wire carrying current up here this way, and then beneath it, you had another wire down here, and the beam was being turned in the middle here. And so it turns out that if you put these two wires that carry current, and usually we have them carry current at the same rate, it will produce a very, very straight magnetic field at this location in between them. And it's because of what we said at the beginning, that these dBys end up canceling, that this arrangement of having two loops that are separated by some distance will produce this really large magnetic field right at the center. And we now know exactly how strong the magnetic field would be. The size of the magnetic field is related to the radius, which is this distance a right here. No, not x. This distance a right here would be the radius of the coils, and then it's also dependent on the distance x, which in this case would be half of the distance between the two objects right here. So this arrangement is often referred to as Helmholtz coils. Can't remember if you have a homework problem like this. I think you do, where you have two coils that are arranged like this, but the field at the center would just be double this, right? And can you see how also it's really easy to control how strong the field is? All you need to do is to manipulate the current, manipulate the size of these things, but really at the end of the day, you just manipulate the current and you automatically manipulate the field. And that's what the guy was doing in the video, where basically in the center of this, there was a beam of electrons that were being forced to kind of circulate around the magnetic field, if you remember. Okay. Anyone have any questions? I don't remember if I don't think I grabbed one of the example problems for this one. There's this, but this is for Ampere's law. So, you know, I'll let you guys worry about learning how to apply this yourself then. It's not a very complicated equation, right? But it's kind of easy to mix this one up with this one here. So just be kind of careful. I'll put them side by side. Oh, no. Click. Boom. See, they're really similar to each other, right? This is the one for a straight wire. It has the pi inside of it. And this is partly because this produces a magnetic field that's like a circular one. And this is for a loop. They're kind of, if you think about it, what this says is that if I have a loop of wire, if the current goes this way, the magnetic field for this is going to point out of the page at the center. That's the magnetic field. And then if I have a straight line of wire, like this. Here, let's draw it a different way, though. Let's say that my straight line of wire has a current I that comes out of the page. What would the magnetic field for this look like? It would look like a loop. Whoops, I thought I switched colors. It would look like a loop. Isn't that cool? I think that's really cool. If you have a wire that carries current like this, at the center of the magnetic field straight like this. If you have a wire that carries current like this, then it creates a circular magnetic field. And this is kind of at its core what the connection between electricity and magnetism is. Now, in reality, the magnetic field of this is much more complicated, actually. The magnetic field of the current-carrying wire is quite simply just cylindrical like this. But if I was to turn the loop on its edge, so if I take a loop of wire and I draw it like this, for example, I think your textbook kind of has, not your textbook, I think that the, so let's say the current goes this way. I'm not going to do a great job doing this, but I'll try. The magnetic field in this case is definitely going to be straight in the center, so it's going to kind of point up like this. But then the magnetic field lines at other places are going to kind of curve out like this. And there's even a circular magnetic field line that goes around like that. They're all circles, technically. It just depends on how big you draw it. So they kind of go like this, and they go like this. And now I got to think about this. Yeah, this would go this way, this way, this way, this way. Okay, that's not a horrible drawing. You'll find better drawings online, but if you think about it, a loop of wire that carries current produces a magnetic field that's kind of similar to a dipole. It is similar to a dipole. This is exactly what it looks like for a bar magnet, basically. So a little loop of wire that carries current is effectively like a little bar magnet. And this, at its core, is how atoms can have magnetic fields, and how a bar of iron can be composed of a bunch of little atoms that all have magnetic moments that when you add them up produce the magnetic field of the bar itself. Okay, so coils and wires and magnetic fields. We now know something about them, right? We know that current-carrying wires can produce magnetic fields, and we know a little bit about the shapes they can produce. We also know very simple ways to produce magnetic fields that we can control exactly in terms of determining how big the field we produce is, which is really powerful. Okay, so the last topic for tonight, and I'll just try to get through as much as I can. We'll pick up with whatever I left off in a couple weeks, because we have the exam next week, is what's called Ampere's law. So Ampere's law is a little like Gauss's law for current. It's pretty similar. So we have talked about voltage, right? Just to kind of remind you, we said that there's this idea of electric potential, and it can be calculated by doing a line integral of basically E dot dl, or ds, or whatever you want to call it. There's this right here. So we think about this quantity here, and we say, well, what if we did the exact same thing, but we used the magnetic field instead? So Ampere's law asks the question, what do you get when you integrate B dot dl? And the way that I'll come to an answer for this is I'm just going to apply it to a magnetic field that we already know about, okay? So we're going to take a wire, and let's say that it carries positive current coming out of the page towards you. Around this wire, I'm going to put a ring. Like that, centered on it. And I'm going to kind of evaluate what B dot dl would be around this curve, okay? So B dot dl is a line integral. And my dl's point like this. And what direction does the magnetic field point? Well, we know that the magnetic field for this wire right here, this is a long wire, it's carrying current coming out of the board at you, is going to produce magnetic field lines that basically point just like this. The magnetic field also points in that same direction. And if I was to come right to this point right here and try to draw a magnetic field, it would point like this. So they'd be parallel to each other, right? So let's evaluate this integral, and let's do it all the way around the loop here, okay? So our integral says to take the integral of B dot dl, we're going to do it all the way around the loop. The first thing I notice is that B and dl are parallel to each other at all points. That allows me to remove the dot product and merely turn this into B times dl. We're going all the way around. The other thing I can say is that at a fixed radius here, so if I define the radius of this to be r, at a fixed radius, the magnetic field is constant, so that can be pulled out of the integral here. And we just end up integrating dl. What this becomes is the circumference of this circle, right? A line integral around adding up every single line element here. This ends up becoming b times 2 pi times r. But what's b equal to? Well, we already found by using the Biot-Savart law that the magnetic field was equal to b divided by 2 pi times r. So that's kind of remarkable. Look at that. The 2 pi r's just kind of cancel out. And we get that the answer is mu naught multiplied by I. So what is Ampere's law? Ampere's law states that if I integrate the magnetic fields around a closed curve, what do I get? I get this. I get mu naught multiplied by I, and it turns out that what matters here is the current that's actually enclosed by the loop. Whoops. The current that's enclosed by the loop. So I enclosed is, I'll say it's the sum of all currents that pass through any surface what's the best way to say this? Enclosed by the loop? I think it's any surface that's bounded by the loop. Any surface that's bounded by the path of integration. So I enclosed is the sum of all currents that pass through any surface bounded by the path of integration. And that is Ampere's law. The fact that it has the current enclosed, or the current passing through, is why I say it's kind of similar to Gauss's law. We define the direction of the current to be positive if the current flows in a way that is consistent with the path, i.e., according to the right-hand rule. So in this case, the current would be positive, okay? But if we flip the direction of the current, it'll become negative. You'll actually also get a negative for the integral too. But in general, what you want to do when you do this integral is you kind of want to make it so that your currents are positive by taking the integration path in the same direction as the magnetic field, if that makes sense. So, yeah, there we go. That's Ampere's law. Let me kind of tell you some caveats of this here. So let's say that we have a path, and let's say our path is this. So that's our path. Path for the path integral, the line integral, what do you want to call it? And within this region here, I place some currents. So like maybe I've got a current here that's 5 amps. Maybe I've got a current over here that's going into the page, and it's, you know, maybe like 3 amps. And maybe there's another one here that's 1 amp. You could ask, along this path right here, what would the value of this integral be? And Ampere's law can tell us the answer. I've got a 5 amp current coming out and a 1 amp current coming out. The path direction, according to the right-hand rule, automatically makes these positive, and it makes this one negative. So you end up getting 6 amps minus 3 amps, which is equal to 3 amps. Of course, this is also multiplied by mu naught, so this would be the value. Does that make sense? It's just like positive and negative charges in a way, right? Currents coming outwards are going to be positive, currents going inward are going to be negative, but it's dependent on your path direction, if that makes any sense. That's Ampere's law. Anyone have any questions? When I say the sum of all currents that pass through any surface bounded by the path of integration, I don't know if that makes sense, what I'm saying, but what I mean is I take my path here, right? What's a surface that's bounded by that path? Well, it'd be something like this. That's a surface that's bounded by the path, right? But I could also bend it if I wanted to. You know, think about like a trampoline. Imagine you put a bowling ball in the center of a trampoline, it's going to droop, right? But the surface of the trampoline itself would still be bounded by the kind of springs that are supporting it. So this surface can bend. And that will be important later on. Like I say, this is the third of Maxwell's laws here, right? The other two that we've learned so far are Gauss's law, which says what happens when you integrate E dot dA. And the answer to that is you get Q enclosed over epsilon naught. That's Maxwell equation number 1. Second Maxwell equation is Gauss's law for magnetism. It says that when you take the surface integral of the magnetic field across the surface, you get the magnetic flux, and this is always equal to 0 because there's no such thing as magnetic charges. This is the third one, Ampere's law, which states of what happens when you do the integral of B dot dl. and we find out that you get mu naught times I enclosed. The fourth Maxwell equation, I'll tell you right now, is related to this. And what it says is what happens, well, I mean, you can see that it's consistent with this. It talks about what happens when you do the integral of E dot dl. We already know that it produces this thing that we call EMF, okay? But it turns out that that EMF, so you can see some similarities right here, this is also equal to something else. And we'll learn what that is next time. It's called Faraday's law. It's equal to the derivative of the magnetic flux, technically negative derivative of magnetic flux. So that's Maxwell's equations right there, okay? But one thing you might notice is this is called Gauss's law, both of these. We just said this one's called Ampere's law. And we're going to learn that this one's called Faraday's law. That's the next chapter, okay? So why do we call them Maxwell's equations, then? Does anyone know? Something to think about. Why do we call them Maxwell's equations? Maxwell used them for something? I don't know. Maybe. I'll tell you a hint, which is that this doesn't tell you the whole story of this equation. Ampere missed out on something. Ampere missed out on something. Yeah, that's pretty much right, Ash. But there's a little more to the story, which is Maxwell actually created a correction to this. There's another term here that's missing. There's a missing term right here. So yeah. Okay, but you're all right that he did. Anna said that he combined them, and Ash said that he took them and then, you know, what's G? Miguel. G with a question mark. What's G? Oh, okay. All right. So we want to use this to solve these two problems here. We only have time to do one, so we're going to do the solenoid. Oh, a missing variable. Yeah, so contained within what Maxwell figured out is within these words right here. It's the any surface part, and he's going to apply it to a capacitor. Okay, so let's do this problem right here. This isn't so much of a problem as this is a derivation, actually, but in your book it's a problem. Okay, so let's talk about this. We're going to find the field of a solenoid. This is something that's going to be very, very useful to you. And what we basically like to prove is that the magnetic field for a solenoid is given by mu naught times the number of turns per unit length. That's what we want to prove. We want to prove this. Now, what is a solenoid? A solenoid is something that you may have heard of existing in your car. When you start the car, there's a solenoid there that sometimes might have to be replaced. A solenoid is a very complicated word for basically just a bunch of coils wrapped around a core. Okay, so if you have a setup where you've got some coils of wire that basically are arranged like this, kind of looping around, and there's often some kind of solid core right here, but that's what a solenoid is. The current kind of flows like this, and what we know about the solenoid is if the current's flowing kind of in this way, up this way, in this way, up this way, that each of those little wires are loops, and we can say what the direction of the magnetic field that's produced by them are, and I'd say in this case that you get a magnetic field just as we see in that picture up there. It's going to be straight. So a solenoid has the advantage of producing a very uniform magnetic field inside of the solenoid. So in a way, it's kind of the analog to the capacitor for magnetism, right? Because if you remember what a capacitor does, a capacitor takes two plates, one that's positive and one that's negative, and it produces a very straight electric field in between the plates, right? Like this. So a solenoid and a capacitor are similar in the sense that they produce straight fields inside of them. The solenoid produces a magnetic field, the capacitor produces an electric field, right? So they're both kind of important components for electrical systems. And what we'll see is that the solenoid itself, or just the act of coiling up a bunch of wires like this, will actually allow us to store energy inside of a magnetic field in a circuit, and it will form the last of the kind of static circuit components, passive circuit components. We learned about resistors, capacitors. This thing is going to have another name. We're going to call it an inductor. Any coil of wire is going to be called an inductor, and we're going to store energy inside of that, just like we store energy inside of the capacitor. Before we get to all that stuff, we need to understand how to actually find the magnetic field of the solenoid. So what's been done here is this kind of coiling of wires. We've cut a plane through the center of it, and they've drawn up here a picture of the solenoid. But we're really just seeing, you could probably imagine, so like, I'm going to draw on this picture, but then I'll erase it. What's happening here is you have current flowing out here. These are all currents, okay? You've got current that flows out here and then into there, and then it comes back out here and then into there, and then back out here and into there, and it's looping back around. Does that make sense? Current comes out this way, and then it goes in there, and then it loops back around, then it comes out this way, and then it goes in there. Then it loops back around, and it comes out this way. And we're just kind of cutting that whole thing in half so we can see a little bit better picture of what's going on. Okay? Does that make sense? Now we're going to make a couple of assumptions here. We're going to say that the field is mostly confined to the inside, and that the magnetic field in the region out here is going to be 0. Okay? And what's drawn here is an integration path for us to use. We're going to be applying what we just learned. What I just wrote on the board. I don't know if you guys learned anything yet, but maybe after doing this problem, you'll have a better understanding of what this equation does. We're going to use Ampere's law to solve for the magnetic fields. Okay? All right. We've already got 2 of the pieces, right? Mu naught and I, they're already there, so we just got to get an n over L here somehow. All right, so here's what we're going to do. We're going to do this line integral. We have to go around a closed path, right? All the way around the closed path. So we'll go from A to B, and then from B to C, and then da-da-da-da, okay? Our integration path is going to be broken up into these DLs, so I'll just kind of indicate on here that this is an example of what our DL would be on this side. This would be the example of our DL on this side here, and then DL up here would be like this. Now, it's kind of a lie that the magnetic field out here is 0, but it's not a bad lie. And the way they've drawn this picture with these jagged lines, they're saying, suppose that we make our loop of integration so big that these are so far away that there is no magnetic field out here. Close to the solenoid, there's going to be some small field out here, but the fact of the matter is most of the field exists on the inside. Okay. Yeah, let's do this. So we need to break this up into, like, basically 4 pieces here. So we're going to need to integrate b.dl. We're going to have to go, I don't know if this is a good way to do this, but I have to go A to B, plus we got to go from B to C, plus we got to do D to A, and then plus we also have to do, wait, A to B, B to C, I left out C to D. So we're going to be performing that operation on all of these pieces. B.dl for all of them. I don't know why I feel bad about A to B here. It's a weird way to think about this. They're not really limits. We're just going from A to B, basically. Okay, what's B.dl going to be on the inside here? Well, we're going to basically tell you that B is constant in this region. And you can pull it out. The magnetic field points to the left and DL points to the left, so we don't really need to do anything with that. So we really just end up integrating DL, which for this, what that's going to mean is it's going to be B times this length L here. So this becomes B times L. For B to C, the magnetic field points to the left and these point this way, so when you do this, you're going to end up getting B times DL times the cosine of 90. So that's going to be 0. For a similar argument from A to D, or D to A over here, this is also going to be 0. And then out here, the magnetic field is 0. So that's going to be 0. Okay. And all of this should be equal to, now I left something out here, it's mu naught times I, but, and we're going to say the current flowing here is I, but what I'm going to say is that if you look at what's happening here, there are 1, 2, 3, 4, 5, 6, 7, 8. There's 8 i's there, right? So I'm going to multiply this times 8 times I. There's 8 currents that flow out of this thing. And they flow in, but the direction of our loop makes those positive. Because if you point the thumb of your right hand in the direction of those currents, your hand would sweep in the same direction that we're going. So the magnetic field then is equal, this is mu naught, is equal to mu naught times 8 divided by L times I. So what does 8 over L represent then? Let's say that the entire solenoid has a length that we call this little curly L right here, right? 8 was the number of wires that we had coming out here, coming in there, and we divided by L. But I would argue that it looks like that these things are equally spaced from each other. So I would say that if the total number of turns in the solenoid was n, so if n is the total number of turns, I would argue that if I take the total number of turns and I divide by the total length of the solenoid, that should be equal to 8 divided by L, or 5 divided, whatever number of currents we happen to have here. So then this ends up becoming mu naught times the total number of turns divided by the total length multiplied by the current I. And that is what you're trying to prove. That's the magnetic field of a solenoid. Another way this is commonly written is that you take a little n here, so that little n represents the number of turns per unit length. And this will often be something that's actually written on a solenoid, is how many number of turns per unit length you have. In that sense, it's equal to that. This gives us the other version of this that we'll also use. And there we go. Does anyone have any questions about that?